why should the sum of all the shape functions for an element be 1? We know that we use shape functions to get the displacement at any point within the element from the nodal values. Basically, we use shape functions as a interpolator functions, and we interpolate the nodal values to get some value within the element. Now, while assuming the shape functions or while deriving the shape functions, what we do, we use some trial functions or some approximate functions, and then we satisfy some conditions, and at the end we try to get our displacement functions, okay, in the n1 u1 and in the form of n1 u1 n2 u2, like that. Okay, if you have two noded elements, in that case we can write our displacement functions in this form, where n1 and n2 we used to get as a shape functions. Okay, now for some standard element, we know what the shape functions look like. For example, if you have two noded element, in that case, if you write the shape functions, we can write the shape functions in this form, right? N1 is equal to x2 minus x by L, N2 is equal to x minus x1 by L. Now again, if you want to write the same thing in our natural coordinate systems, in that case, we should write our shape functions in this way. Now, if you consider four noded element, in that case, our shape functions look like this. Okay, so this is very standard formula or the shape function for known element. Now, if we want to derive shape function for new element, in that case, you have to use some approximate functions and you have to apply some boundary conditions. From there, we will obtain our shape functions. Now here, the assumptions of the shape functions are not arbitrary. Okay, the way we obtain the shape function is not arbitrary. Shape functions need to satisfy some conditions. For example, if we have a bar, okay, and it deform like this, then deformations should be continuous in the inter-element connection. Deformation at least should be continuous in the inter-element connection. Okay. Now, in some cases, it may happen that our strain also continues in the inter-element connection. Okay. Now, question is that why the deformation should be continuous? Now, here you just see the scenario. We have a bar and it is deformed like this. So, in this point, either you calculate the displacement here or you calculate the displacement from this element. Here, in this point, the displacement should be one single quantity. Okay, one single quantity. Now, if the displacement is not continuous, in that case, whatever the displacement we will calculate from this side, that will be one value, or if you calculate displacement from this side, that will be another value. Okay, so now what happened, if the displacement is not continuous, then we will not have our desired shape for this particular problem. Okay, similarly, we will observe that in some cases we have a demand of strain to be continuous in the inter-element connections. Okay, so in that case we have to basically assume some higher order element. In that case we have to assume some higher order element. So here we have discussed that our shape functions need to satisfy some criteria. So apart from the deformation shapes, shape functions also need to satisfy some criteria, that is your rigid body motions. So if you have a bar like this, and if you do not apply any boundary conditions, and if you want to get our mode shapes or eigenvector, okay, in that case, our bar also should show rigid body motions if there is no boundary conditions. Okay, if there is no boundary conditions, in that case, our bar should show the rigid body motions. Okay, now we'll see how that summation of unity is basically leading to this point. Okay, so here what we do, we assume a bar. Okay, in this bar there is no boundary condition, and this is our reference point. And this bar is subjected to a rigid body displacement of amount c. So basically, our node 1 will have a displacement of c amount, and node 2 also will have a displacement of c amount. Okay, now since this body has a rigid body displacement of amount c, then we can write u, okay, the displacement of the body as equal to c, displacement of the body as equal to c. Again, you can correlate our displacement within the body through our shape functions in this way, n1 u1 plus n2 u2 for this bar problem. Okay. Now here our n1 is the shape functions and ur is the nodal value, n2 is the shape functions, u2 is the nodal value. So basically here you can see again we are interpolating our nodal value to get our displacement. Okay, now here you just see that for the rigid body motion, the displacement u is also c. Okay, now we can write it here and we can do some mathematical simplifications. So if we do some mathematical simplification, what we will get? We will get our c is equal to n1 u1 plus n2 u2. Again, the value of u1 that is equal to c, value of u2 that also is c because the body has that rigid body displacement. Now we can write that our 1 that is equal to n1 plus n2. Okay. Now here you can see that to satisfy the rigid body motion criteria, in that case our shape function also should satisfy that condition that sum of all the shape function of a element should be 1. If we do not satisfy that conditions, then that element will not be able to represent the rigid body motions. Okay, so basically other way you can say that element may not be generalized element. Okay, so apart from the deformed shape, apart from that continuous displacement or the continuous strain cases, that element also should represent the rigid body motions to have a generalized element. Okay, so now what happened? Phenomena, this phenomena also known as partition of unity. Okay, and this is required for the interpolations to work properly. So if we go through that term partition of unity, we'll observe that to have the proper interpolations, okay, our partition of unity condition should satisfy. So here in the finite element method, this is basically we represent as a sum of the shape function is equal to 1. Okay, so I hope you get some idea that why should the sum of all the shape functions for an element should be 1. Thank you.